This video is about the organic family of alcohols. You'll see that I wrote the ROH, and you may recall from our haloalkane lesson that the R group is a hydrocarbon. So we're pointing out here that there's a functional group made of an oxygen directly bonded to a hydrogen, and we call this functional group the hydroxyl group. So molecules that contain a hydroxyl group are members of the family of alcohols. Applying what you've learned already in the physical properties lesson, if you have a look at the ROH group or molecule here, and then a second ROH here, you'll notice that there's a capacity for hydrogen bonding between the molecules, which is going to increase the boiling point. So a 2-carbon alcohol is definitely going to have a higher boiling point than a 2-carbon alkane, alkene, or alkyne. On the solubility side of things, the alcohol would be interacting with water, for example, as the solvent. And you'll see that the water molecule has the ability to be hydrogen bonded by this oxygen, and similarly the oxygen on the water molecule can form a hydrogen bond with the hydrogen of the hydroxyl group. So since those hydrogen bonds are able to form, we will see solubility in water. Now in particular for smaller alcohols. So you'll notice here small molecules are soluble in water. Once you get to larger alcohols, the length of that hydrocarbon chain, which is nonpolar, is definitely going to be dominant in determining the solubility. And so as that hydrocarbon chain increases, we definitely see a decrease in the solubility of the alcohol in water. Even though we still have that polar OH group, which has the ability to hydrogen bond with water, the rest of the molecule is very nonpolar, and so the water won't be able to interact with that part of the molecule. Later on in a lesson, we will see some reactions of alcohols, and the classification will be important at that point. So just to help you out with that, we have primary, secondary, and tertiary alcohols. And that's what these one with a circle superscript means. So this refers to primary, secondary, and tertiary. So you'll see the 3 examples below. I'd like you to pause the video and see if you can come up with a definition for the primary, secondary, and tertiary alcohols. So how do we decide which is which? Okay, so compare your explanation to mine. You'll notice that I've used red to make a dot on the carbon that is directly bonded to the oxygen of the hydroxyl. So I've done that here, here, and over here. So now take a look at how many carbons this carbon is bonded to. 1. Take a look at how many carbons this carbon is bonded to. 1, 2. 2. Secondary. And this carbon, again, the one where the OH is attached, is bonded to 1, 2, 3 carbons. There's your tertiary. So the concept is that the carbon that the hydroxyl group is bonded to is itself bonded to either 1, 2, or 3 carbons, creating the primary, secondary, or tertiary classifications. Okay, for naming. Really, there's just a few important points at the beginning, and then everything else you've learned is the same. So for alcohols, there is a suffix. That suffix is "-ol". So that might be easy to remember thinking of the name alcohol. So the OL at the end is the suffix for the IUPAC naming of alcohols. You will need a number. So the suffix needs a number when there are 3 or more carbons in the parent chain. So propane and up, we need to number the presence location of the hydroxyl group. If we're naming the OH as a side group, it will be a prefix in the name and go by the term hydroxy. We'll need to introduce higher priority functional groups in order to be naming the hydroxyl group as a prefix, so that'll be coming in later lessons. If we have multiple hydroxyl groups in a molecule, be prepared to use diol and triol, just like we did before with diene and triene. Just be sure to keep the E of the parent hydrocarbon. In terms of priority, I've now introduced three groups, A, B, and C. You're already familiar with groups B and C, where the double and triple bonds are higher in priority than the alkyl, halo, nitro, or phenyl groups, which are all equal in priority. And now I've put the hydroxyl functional group in category A. So category A is higher in priority than B, which is higher in priority than C. And so the priority runs from highest to lowest, A, B, C. So if we have an OH group and a double bond, the OH group, whatever carbon that's attached to, will get the lowest possible number. If you have a halogen and a hydroxyl group, whichever you want to number so that the OH group gets the lowest possible number. And that's really the only thing that's left to learn. So let's try these examples. Perhaps you want to work ahead of me because you've already got a good idea how this works. I'll explain the first few and then you can pause whenever you need to and start trying the questions. So, as before, I'm looking for the parent chain, noticing that the highest priority functional group is the hydroxyl group. And so I'm going to number to give the the carbon of the parent that's bonded to the OH the lowest possible number. In this case, there's only one carbon, and so the root for 1, M stands for monkeys, so we think of meth. Now the concept here is, think of the name of that hydrocarbon, methane, drop the E, so we drop the E, and then add the suffix OL. So in fact, this becomes methanol. Okay, part B, example B. So we see two carbons. I'm going to number the two carbons to give the hydroxyl group the lowest possible number. So 1, 2. Monkeys eat, 2 stands for eth. So I think of ethane because there are single bonds between the carbons, but I drop the E and add OL. And so we have ethanol, which is the molecule in beverages, alcoholic beverages. Now, just for your information, every compound has an LD50, a lethal dose that will kill 50% of the population. Methanol has a much lower LD50. It doesn't take a lot to cause blindness or other serious health issues. Ethanol also has an LD50, so it absolutely is possible to get alcohol poisoning from alcoholic beverages. So be aware of that when you reach the age and choose perhaps to consume alcohol. Okay, so in example C, again, start looking for the parent chain. Give the carbon of the parent chain that's bonded to the OH the lowest possible number. And because we're at 3 carbons, prop, make sure you number the location of the hydroxyl group. So instead of propane, we drop the E, and now we number that hydroxyl group is off of carbon 1, and so this is propan-1-ol. Okay, so try D, E, and F. Okay, so in example D, I numbered the 3 carbons. In this case, it didn't matter, left to right, right to left. The hydroxyl group was still going to be off carbon 2. I think of propane, drop the E, propan-2-ol. In part E, I purposely numbered from the right because the hydroxyl group needs to have the lowest possible number. Period. That's how you decide. And after that, 4-chloro, 3-methyl, pentan-2-ol. Just as before, I have sequenced the prefixes in alphabetical order, and you'll see the suffix here telling us where the hydroxyl group is located. Example F is a cycloalkane, happens to be 5 carbons in the ring, and so we have cyclopentanol. I don't need to number that OH because it is the only group in the cycloalkane. Okay, moving up to examples G, H, I, and J. So give these a shot and then check in. Okay, so we have a cyclohexane ring with a fluoro, a methyl, and a hydroxyl group attached. The highest priority functional group present is the hydroxyl group, and so that will be the suffix. And in this ring, that will be attached to carbon number 1. And so I must number from that carbon as carbon number 1. So this one right here has to be carbon number 1 because the highest priority functional group is bonded there in the ring. And so from here I have choices to go clockwise, hitting 1, 3, 4, or going counterclockwise, and in which case that would be 1, 2, 3, 4, 5, hitting 4 and 5. So I'm getting side groups on 3 and 4 instead of 4 and 5, and so I will follow the 3, 4. The methyl's on 3, the fluoro's on 4. I sequence them, the prefixes alphabetically, and come up with 4-fluoro, 3-methyl, cyclohexanol. Looking at H, there are 4 carbons in the parent chain, and I number to give the highest priority functional group, which is the hydroxyl group, the lowest possible number. 4 carbons is bute. It's not butane this time. There is a double bond. It's coming after 3, so bute, 3, and 2 all. In I, there are 5 carbons. Numbering from the end closest to the hydroxyl group puts that hydroxyl group off of carbon 2. I see there's a triple bond after 3, and so pent, 3, ine, 2 all. J is our first example of a glycol where we have hydroxyl groups on adjacent carbons. This happens to be the main component of antifreeze, also known as ethylene glycol. But our IUPAC name follows what I put up in the earlier notes. We write the name of the parent alkane, which is ethane, and we keep the E because we're going to have the consonant coming in the suffix. So ethane 1,2-diol. Okay, so next examples, K, L, M, and N. Give these a shot and check in with the video. Okay, so question K, you'll see 3 carbons, OH groups on each of those carbons. Keep the E because the T of the triol is a consonant, and so we have propane 1,2,3-triol, which is actually glycerol. Example L, you see a benzene ring with the 2 OH groups, and so we're naming this benzene 1,4-diol. Benzene with an OH group is a common structure, and it goes by the name phenol. So you need to memorize that that's phenol. You can possibly put that together, the idea of the phenyl and the OL, and we come up with phenol. So in question N, I've named it as a phenol because we have a methyl off of 3, and so that generates 3-methylphenol. Now, if you were to name it as a benzene, then you would say 1-hydroxy 3-methylbenzene. But really you should get comfortable with that phenol root and suffix. Okay, last part of the lesson is the reactions. So how do we actually prepare alcohols? Well, hopefully you're familiar with the idea of hydrating alkenes, right? You've seen this before. An alkene plus water will undergo an addition reaction to produce an alcohol. That doesn't really help though for producing a 1-carbon alcohol because you can't have a 1-carbon alkene. So how do we make methanol? Well, carbon monoxide and hydrogen gas react to form methanol in water. Now there are certain reaction conditions, temperature, pressure conditions, which we're not requiring the memorization of, and so I've simply shown the reactants and the products. When wine is made from grapes, the sucrose in the grapes, an enzyme breaks that molecule up and we have a glucose molecule that then undergoes fermentation to form two ethanol molecules together with two carbon dioxide molecules. And that's why if you ever had a tour of a winery in these large, tall tanks where the sugar ferments, you would see vents at the top to allow that carbon dioxide gas to release. There are multiple steps involved in the conversion of the sucrose from the grapes eventually into the alcohol, but this would be the summary of it. The glucose forms the 2-ethanol plus 2-CO2. Okay, so having said that, the alkene hydration reaction here is going to be the most common prep method for you for alcohols. Okay, so what are the chemical properties then? How do alcohols react? Well, you're going to find there's quite a number of options here. For A, B, and C, we'll explore these in a later lesson. So for now, just take note of them. Learn that they're called oxidation reactions. Primary alcohols oxidize to aldehydes, releasing water. Secondary alcohols oxidize to ketones, releasing water. And tertiary alcohols do not oxidize at all, and so NR stands for no reaction. I'll go into those oxidation reactions in detail when we do aldehydes and ketones. Okay, part D is the reverse of the hydration reaction. You'll see this is an elimination reaction. So an alcohol can be made to revert back to the alkene and water. In part E, you see a condensation reaction. Two alcohols come together to form a new family that you haven't seen yet called ethers. Water is released. So I show a specific example here of methanol. So you see CH3OH and propan-1-ol. And you'll notice that I purposely put the hydroxyl groups facing each other so that I could box out an H from one hydroxyl group and the OH of the other to show you the water that's being formed as these two molecules condense to form an ether. So the ether linkage is this COC connection that shows up in our organic product. Just a comment about the R here and R primed. The only reason I'm putting a prime there is just to indicate that these two R groups do not have to be identical. So in this example, I showed a 1-carbon alcohol and a 3-carbon alcohol, but it's possible to have two methanol molecules condense to form an ether, but the idea is that the length of the hydrocarbon chains in these two molecules can be different. The last example is a combustion reaction, and I've written it out for you with the complete combustion product, so why don't you take a moment to balance this equation. Okay, so I'll go through the balancing just in case you found that tricky and need to hear how I thought through it. So I notice on the left side, well, first of all, for combustion reactions, we always balance C, then H, then O. So you'll notice here that I see 3 carbons on the left side of the arrow, so I come over here and notice 1 carbon there, so I'm going to put a 3. Then I look at the left side for hydrogens, and I notice there's 7 here plus 1 here, so that's a total of 8 on this side. I come over to the other side and see a 2, so 2 times 4 will be 8. Now, having placed the coefficients in the product side right here and right here, I have fixed the number of oxygens now on the right side. So I'm going to see what that is. 3 times 2, there's 6 here, and 4 times 1, there's 4 here, and so I have a total of 10. So I come back to the left side and realize that the alcohol molecule actually has 1 oxygen. So if one of those oxygens comes from this molecule, then the remaining 9, so that it equals 10 on the left, the remaining 9 have to come from the O2. And seeing as 2 times a number is not going to equal 9, using a whole number, I recognize that I cannot leave the original alcohol here blank or with a coefficient of 1. That's not going to work. And so the idea is then to erase the work that you've done and start over again, but this time start with a 2 on the original, as the original coefficient for the alcohol. And by doubling this now, I see that 2 times 3 is 6, so I come over here and 6 times 1 would be 6. So carbon's fine. 7 plus 1 here for the hydrogens is still 8, and 8 times 2 is now 16 hydrogens. So I come over to this side and think 2 times 8, 16. Now that I've fixed the oxygens, I notice 6 times 2 is 12, and 8 times 1 is 8, and so 12 plus 8 is 20. And I come back over to the left side and notice that the 1 oxygen in the alcohol now multiplies by the coefficient of 2, and so there's actually 2 oxygens from the alcohol, and so then the remaining 18, which would equal 20, need to come from the O2 molecule. And so 9 times 2 is 18. So just be prepared. Sometimes you'll need to raise the coefficient of the alcohol to a 2 and go through the process again. But hey, if it balances the first time, then you're good. Always when you're balancing, check at the end to see if the coefficients are a lowest terms ratio. So 2 to 9 to 6 to 8. There's no number that I could divide each of those by and have no remainder. And so 2, 9, 6, 8 is the ratio in lowest terms. Okay, that's it for alcohols.